please make sure that if you have a microphone that's active, that you mute it so we don't get a lot of noise in the background for the recording. And I'll try and mute you from here also, just to make sure. Sometimes that works, sometimes it doesn't. Okay, I'm gonna take kind of a step back and look at this a little bit more simply. And let's just, for starters, talk about probability. Okay, and this is on Blackboard right now. I might have modified a couple of these documents. So the most current version right now is on Blackboard. But let me talk to you guys too, since you're here. Let's take a look at just simple probability. Okay, we spoke about the idea of independence and exclusivity, right? So we're going to look at a few problems that involve a situation where we're interested in the probability of certain outcomes, right? So I'm going to look at the probability that a person is insured. So let's say we're working with a population where 80% of the population is insured. That's probably pretty close to what it is in New York City right now. Maybe it's even a little bit more, right? So let's say you chose one person randomly from that population. What's the probability that that person is going to be insured? It's going to be 80%, right? That's pretty clear, 0.8. Okay, good. Well, how about if you choose 3 random people from that population? What's the probability that all of them are insured? Well, first of all, first thing is that the random sample suggests that this is probably an independent event. In other words, if you're really picking these people randomly, then the probability the second person is insured is not influenced by whether the first person is insured or not, the third person, and so on and so forth. If we were to just stand out on the street and grab the first 3 people that came along, that might not be so true, right? They might not really be an independent sample because maybe they work together, right? And if they work together, they might have the same insurance program. It might be more likely that they're insured. If they're married, then both of them may be insured by the same company because one of them is insured and so on. So that may not be truly independent, but a random sample like this, let's assume for a moment that it's really that these are independent events, right? So what's the probability that it's 80% that any individual is insured? What's the probability that 2 of the people would be insured? Both people will be insured. Let me put it that way, right? It'd be 0.8 times 0.8, just like flipping a coin, right? I mean, let's go back to flipping a coin, right? If I flip a coin, what's the probability of my getting heads? It's 0.5, right? If I flip a coin again, what's the probability of my getting heads on that second coin? It's 0.5, right? They're independent events, right? So what's the probability that if I flip 2 coins, right, without stopping, that both of those would be heads? Well, how many possibilities do I have? The first coin is heads. The second coin is heads. That's one possibility, right? Second possibility, the first coin is heads, second coin is tails, right? Another possibility, first coin is tails, second coin is heads. That's third possibility. Fourth possibility, they're both tails. So there's one possibility that there's one outcome that satisfies my requirement that they're both heads. And that's 1 out of 4 times this is going to occur, right? How many of you guys go to casinos every once in a while? No, nobody here admits going to a casino every once in a while. How about the track? Nobody goes to the track or OTV or anything like that. No, boy, well, no wonder you're finding this so difficult. So at any rate, yeah, you need to spend more. You have to be railbirds. You have to spend more time at the track. So at any rate, so think about that. 1 out of 4, one possibility satisfies the 4 possible equally likely outcomes. So it's 25% probability that both of them would be heads. And how would I get that? 0.5 times 0.5, right? So let's go back to our insured people. What's the probability that if I pick 3 random individuals from this population, all 3 of them would be insured? Be 0.8 times 0.8 times 0.8. What does that come out to? Anybody want to quickly calculate that for me? What's that? 51%, right? 0.51. Okay. What's the probability that all 3 of them would be uninsured? 0.2 times 0.2 times 0.2, right? The probability any of the individual being uninsured is 0.2. And for 3 of them being uninsured, it's 0.2 times 0.2 times 0.2, right? This is a multiplication rule, right? And what's one of the issues that one of the things we're concerned about here is that they're really independent events. Okay, so what's the probability that, let's see, you choose 10 people from a random population, it's probably all 10 are insured, right? 0.2 to the 10, to 0.8 to the 10th power, right? 0.8 times 0.8 times 0.8 times 0.8 times 0.8 times 0.8. Okay, and again, probability that you randomly choose 10 of them, and okay, you repeat. Now let's say we do this. Let's say we sample 3 people, and we check to see if they're insured. So probability that all 3 are insured is 0.8, right? So now what about if I keep doing this all the time? Like, in other words, I sample 3 people, right? The probability that all 3 of them are insured turns out to be, I think the population is, let me back up 1 second. Let me rephrase this. The population, the 80% of the population is insured. I randomly select 3 people and ask them if they're insured. I do this once, right? So I may find that it's 80% likely that all 3 of the, 0.8 times 0.8, 0.8, which is 51%. 51% of the time, all 3 of them will be insured. But a lot of times, I won't have all 3 people insured, right? So now, let's say that I repeat this 1,000 times to check what percentage of the time that I find that all 3 people are insured. So if I did this 1,000 times, we would expect 51% of the time to get that outcome, right? So what happens if I find out that 75% of the time all 3 people are insured when I do this 1,000 times? What does that suggest to you? That this wasn't really independent, right? So that might be a test on independence, right? Whether or not you get if you repeatedly do this, if you take a large sample and repeatedly do this, whether or not you get the outcome that you would expect for 3 people being insured. Okay, so keep that in mind, because maybe something will come up in the future that might ask you to think about, in a certain situation, whether an outcome suggests that events are really independent. Okay, so let's take a look at another possibility. What's the probability? Let's say the probability, same population, probability of being left-handed is 20%. So what's the probability that a randomly selected person is insured and left-handed? What do you think that would be? Well, it's 80% that they're insured, 20% that's left-handed. Is there any association? Do you think there's any association between being left-handed and being insured? Probably not, right? They're mutually exclusive. One doesn't affect the other. So what would we expect the outcome to be here? 0.8 times 0.2. So in other words, 16% of the people that we would sample from this population would probably be left-handed and insured. Okay? Okay, this is not hard, right? Are we comfortable with this so far? Okay, good. See if we're okay online. Oh, I'm getting a few answers up here too. Okay, good, excellent. Okay, good. So we're talking about whether things are independent, whether things are mutually exclusive. So I'm going to move on to another possibility, another situation here. Okay, let's make this bigger. Okay, maybe even make it a little bit bigger than that. Okay, I'm going to go back to my coin. Okay, toss a coin 3 times. Probability that all 3 tosses are heads was, again, what was it going to be again? 0.5 times 0.5 times 0.5, which is 0.125, right? 1/2 times 1/2 times 1/2 is 1/8, which is 0.125. Okay, what's the probability that all of them would be tails? Well, there's only one way for that outcome to occur. Is you get 0.5. Each one has to be 0.5 times 0.5 times 0.5 is 0.125. Now, what's the probability that after three tosses, you have exactly one head and two tails. Well, things just got a little bit more complicated, didn't it? Right? Because before we talked about an outcome that was such that all three had to be heads. There's only one way that it can happen. It has to be heads, heads, heads. If I ask you now, what's the probability that only one is heads, exactly one is head and two is tails? There's a few different ways that that can happen. It could be heads, it could be heads, tails, heads. It could be tails, heads, heads. It could be heads, heads, tails, right? There's several ways that you can get that outcome, right? So this gets a little bit more complicated. So what we're going to do now is we're going to sketch this out. We're going to sketch out what the probabilities are and how many different kinds of outcomes that we might have. So I'm going to, here's like, okay. How much room here? A lot of stuff. Okay. Oh, good. 0.18. Well, not 0.18, right? 0.8 times 0.2. 0.16. Are we agreed there online? Oh, it is 0.16. I'm sorry. So tiny on my screen that I couldn't read it properly. Okay, let's see if this is working. Oh, looks like it might be. All right, so I'm going to start out with the possibility with the first coin toss. Here's my first coin, right? There's two possibilities here. That first coin toss, the result could be heads or it could be tails. Okay, let me just, could be heads or it could be tails. Okay, so let's take a look what happens with the next coin toss. Well, the next coin toss, the outcome could be either heads or tails. Again, and had the outcome been tails, the next coin toss could have been heads or tails. And had the outcome been heads, then the next coin that we toss could have been heads or tails. And heads or tails, and heads or tails, and heads or tails. Okay, so what's the probability for each one of these outcomes? What's the probability that I would have gotten heads or tails on the first coin toss? 0.5 and 0.5. What's the probability that on the second coin toss I would have gotten heads or tails? 0.5 and 0.5. So all of these probabilities are the same. Right? I'm going to sketch them all out here. 0.5, 0.5, 0.5, 0.5, 0.5. Okay, so what's the probability that I would get all three heads as the outcome, as one possible outcome? Would it be 0.5 times 0.5 times 0.5 would give me three heads, right? And that is 0.125. Okay, what's the next possible outcome here? I could have had heads, heads, tails, right? So that's two heads, right? What's the probability of that outcome? 0.5 times 0.5 times 0.5 is 0.125. Okay, well, how about heads? I got head, tails. How about heads, tails, heads? Okay, that's two heads also. Probability is 0.125. And heads, tails, tails, that's one head, and the probability is 0.125. Right? And again, now we're going to do the same thing in this direction, except this time we're going to go tails, heads, heads. So that's two heads, 0.125. Tails, head, tails, that's one head, 0.125. Tails, tails, heads, that's one head, 0.125. And tails, 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 that's no heads, that's 3 tails, 0.125. Okay, so let's take a look at this. Let's see. This represents all the possible outcomes. They all have an equal likelihood, right? So I have 1, 2, 3, 4, 5, 8 of them. Not surprisingly, what do they add up to? 1. So we have all the possibilities accumulated here. So what's the probability that I would get 1 tail and 2 heads? Well, 2 heads is really what we're looking for here. That outcome is here, here, and here, right? So if I add 3 of them together, what do I get? I get 0.375. The probability of getting 2 tails would be 1 head, 0.375. And the probability of get all 3 would be 0.125 for heads and 0.125 for tails. So the probability of getting 1 tail, actually 1 tail and 2 heads is 3 out of 8. Right? So it's 0.375. So if I were to ask you, what's the probability of getting of tossing 4 coins or 12 coins or 15 coins? Things are going to get pretty, first of all, number one, going to run out of space, right? So it's going to be silly to do this. So we're going to talk about formulas later on that we're going to use to examine how we can calculate these kind of outcomes without having to draw this elaborate tree. Although I'm going to draw one more tree just to give you a demonstration of something else anyway. Okay, so this is an interesting situation though. Well, how many outcomes did we have for each coin toss? Right? How many possibilities? Each time we tossed the coin, how many possibilities were there? Were 2, right? So that's dichotomous, right? There's variables dichotomous. Could be either heads or it could be tails, right? It's exclusive. It's got to be one or the other. It can't be both. It's got to be just heads or tails. Unless it lands on the edge or something like that, we're not counting that, right? So they're exclusive. So in each event is independent of the one that the coin. Each coin doesn't know what the previous coin was. So okay, so so there are 2 possible outcomes, right? So it's interesting the way that this kind of distributed itself, right? It seemed like the most likely outcomes are something in the middle. For instance, if I tossed 100 coins, how many of those would you think would be heads out of 100 coins? How many of those 100 coins do you think would likely be heads? What do you think? It's not a hard question, right? About half of them, right? You'd expect half heads, half tails, right? Would that occur every time? Right? No, probably not, right? I mean, yeah, really, if you think about it, if you toss 100 coins, what's the probability of getting exactly 50 heads and exactly 50 tails? Doesn't seem that likely, does it? However, the most likely outcome of all the outcomes is 50-50, right? 50 heads, 50 tails, right? So, hi.
I'm just thinking, look, 1 second. So
You're checking our air conditioning?
Yes.
Oh, good. Excellent. So it's working this week.
It's working good.
It's a little noisy, but I don't think you can do anything about that at this stage unless you rip it out and put a new one in.
Sorry.
Take it. Thank you. It's at any rate, at any rate, it is noisy, isn't it? At any rate, or is it just that you guys are so silent that it seems noisy, right? Give me a little enthusiasm for this, right? So the problem is you don't like to gamble. If you like to gamble, you'd be more interested in this. So then we would talk about craps, and we would talk about Big 8 and like Yo and Little Joe and all that kind of stuff. So we could really get into interesting stuff. Maybe we will anyway at some point. So at any rate. So it's interesting. This is a special kind of distribution that we see here. So the most likely outcome is going to get 50 heads, 50 tails. I'm just going to worry about heads, right? 50 heads, right? Well, how likely is it that we would get 48 heads, right? Is it more likely we get 50 heads or more likely we get 48? What do you think? It's a little less likely we get 48, right? 50 is like probably the most likely outcome. A little less likely we get 48. What's the likelihood we only get 20 heads? Probably not very likely, right? That's the likelihood is probably vanishingly small that we get only 20. So if we look at that, as we get away from 50, right? The probability as we get further and further away from that most likely outcome, right? The less likely we are to get that percentage, that being the most likely frequent occurring. Let me put it that way, occurring, right? So 50 is most likely outcome, 49 and 51 are next most likely, 48 and 52 next most likely. And as we got further and further away from 50, it's less and less likely that we would get that particular outcome, that number of heads out of 100 tosses, right? But not zero. It's never going to be zero because always a possibility we could toss them and get all heads or no heads at all, right? That's a tiny possibility, but that possibility exists. So that's something called, that's a special kind of distribution. That's called a binomial distribution. We're going to talk about that in a second. Matter of fact, I might have the video I can play to just give you a, might as well show you this now. I think I can actually play this without, oh, I'll show you a picture first. This is something called a Galton machine. And the way it works is I'm going to walk away from here. I'm going to walk away from, I'll point at it here so the guys online can actually get a little bit, you can probably see my cursor moving around there, right? Okay, so a whole bunch of steel balls, for instance, or some kind of objects. It's kind of like a pachinko machine. Anybody here know what a pachinko machine is? It's kind of like a Japanese pinball machine, right? You've seen it, right? Yeah, exactly. It's kind of like a Japanese pinball machine, except it's vertical. It isn't like these things that like are, an American pinball machine with all the bumpers and stuff like that. So the deal here is we have steel balls. We're going to drop them down here, and it's going to come straight down here, and it's going to hit a pin. Now, when it hits that pin, it could go either direction. It could go to the left, or it could go to the right. 50-50 chance. It's literally the same as our heads or tails, our coin flip, right? And it bounces off that pin. If it goes to the left, it then hits the second pin. Now it has another choice. It can go to the left or right, each one of those problems. If the pin is placed properly, then exactly 50-50 chance that it'll go to the left or the right. And so on and so forth, bouncing all the way down here and so on and so forth. And then at the bottom, we have bins that actually collect these coins, right? Or these ball bearings or whatever they are. Okay, so I'm going to play you a movie. And this is from the New York Hall of Science in Queens. Anybody ever been there? New York Hall of Science. That's a pretty cool place. It's got a lot of demonstration equipment. It's got a lot of stuff for kids, adults. It's really a pretty good place. Should check it out one of these days. Okay, and let me see if I can't get back to this. Hopefully I can get a version of this that's big enough. Okay, see if this works. Okay, this is at the New York Hall of Science. There you go. And there are the balls dropping in the top and bouncing around. See, each one of them, they can go either direction. And what do you think's happening down at the bottom? Let's take a look what the outcome is. There you go. Pretty interesting, right? Where is most of the outcome? Where the left and the right turns are equal. And it's less and less likely that the balls would make more right turns or more left turns than 50-50. But if you look carefully, you'll see that that middle bin doesn't have the majority of the balls. The majority of balls are on other bins. It's only that the center one is the most likely outcome out of all the other outcomes, right? Not that it winds up with all of the outcomes. So this is a binomial distribution. And we're going to be talking about that a while later. And this is based on, we could calculate how many balls should fall into each one of these slots using our probability tree. Or more efficiently, we could use a formula which represents a calculation which would give us the same outcome as our probability tree. But that formula is so ugly that we're going to wind up using Excel. So when you see that formula, don't freak out. Okay. So that's this device called the Galton machine. Okay, by the way, there is, in about 2 weeks, I think, there is a event at the New York Hall of Science. It takes up the whole parking lot, all of their open areas, the building itself, called the Maker Faire. It's kind of a hackers event. where people go there and they bring their robots, their devices, their experiment, the hydroponics, their all these kind of even there are people there with working on genetic experiments. There are people there working on devices to sense brain waves and to actuate mechanical devices based on the brainwave activity, and so on and so forth. There's a million different kinds of activities going on there. So if you're interested, check that out. It's called Maker Faire in New York City, and it's in a couple of weeks. So at any rate, so this is a Golden machine. Now, get that out of the way. So I just want to point out another possibility here for our table, and that is, in this case, just so you know, it doesn't just work for a situation where the probability is 50-50. It's working this way because it's a binomial outcome, right? So if you look here, in this case, we're looking at the probability that a student would get given the student answers 3 questions, what's the probability that he would get all 3 of them right, 2 of them right, 1 of them right, so on and so forth. The presumption is that he has no idea, right, which one is right. In other words, you've never been in that situation, right? It's multiple choice and you see 5 of them and you have no idea which one. Usually you have some idea that one of them is the wrong one, so you can affect the outcome a little bit better. But we're going to look at this as if you don't know which one, you have no idea which one is right out of the 5 answers, multiple choice answers, A, B, C, D, E. Right? So if you look at our coin toss here, instead of a coin toss, we're looking at our answers. The probability on the first question is that a student would get it right is 0.2. The probability to get it wrong is 0.8. Right? The probability to be correct on the second question is 0.2 and 0.8, 0.2 and 0.8, and so on and so forth for each other possible outcome. So what's the probability to get all 3 of them right? 0.2 times 0.2 times 0.2. What's the probability to get all 3 of them wrong? 0.8 times 0.8, 0.8. Everything else in between is going to be a bit more complicated because there are many ways that can occur, right? And if we look at it here, we can see all these different possibilities, right? So, which is the most, in this case, which is the most frequent possibility? It's that he gets them all wrong because the probability is so much greater. But you can also calculate the probabilities of these outcomes using this the table the same way, even if the probabilities are not all 50%. Okay, so let's move on from there. Now, how does all this impact what we were looking at before with our diagnostic test? Yes. Yeah, exactly. Right. If you have 5 possible answers, you don't know which one's right. Yes, it's 20% chance you're going to be right. Oh, okay. Exactly right. Yeah, exactly right. Okay, so let's take a look at our. All right. Oh yeah, we're going to take a look at probabilities from another perspective also. Okay, so I got a table here. Okay, and this is we've been using this for a while, so it's some ancient version of statistics on the U.S. population. These are on millions of people, right, in the U.S. population, and this is a table, a frequency table that's showing us the number of males and females and their marital status in the U.S. population. In this one, the population was 214 million. That's, of course, people over 18, so maybe the population was 300 million then. It's probably more like 350 or 360 now, right? So this was a few years ago. So looking at this table, we might be interested in considering what the probability is that an individual in the United States would fit into one of these categories. For instance, what's the probability in the United States that a person is divorced? If I randomly sample a person in the United States, right, what's the probability that that person is divorced? Well, how many people in the United States are divorced? 21.7, right. And how many people are there in the United States? Right. So what do you think the probability? About 10%, right? Okay. Good. What's the probability that that person is male? Okay. So the probability, what's the probability that uh, uh, I'm gonna not get to that yet. What's the probability that if you randomly sample a person in the United States, that that person is male? Just forget about whether they're divorced or not. What's the probability that that person is male? How many males we have? 100, exactly, out of 214, so it's a little under 50%, right? Okay, good. Okay. What's the probability that a person is male? If I randomly sample people in the United States, one person in the United States, what's the probability that person is both male and divorced? 9 million out of, right, there you go. So what is that about? Like 2%? No, what am I'm saying 10, that's about 4%, 4 or 5%, right? But you can do that math. Okay. Okay. What's the probability that a person is both male and a widower? Let's see, male and widower, right? It's okay. Okay, good. Okay, and finally, for this last one, what's the probability that a person, given that a person is male, what's the probability that he's married? Why is that a little bit different? We just spoke about that, right? It's a little bit different because it's a conditional probability, right? So the condition is we're only choosing among people that are male. We want to know what the probability is that he's married. Okay. Given that he's male, right, which means he's going to be in this line here, what's the probability that he's married? Right? Well, we have 63.5 million divided by, what's that? Right, out of 104.9, right? So, right, because we only are considering males. Given that he's male, right, which puts him in this group, what's the probability he's married? So it's 63 over 104. Okay, how is that different? That's a conditional probability. Let's fly without a net. Remember that formula you were looking at before? Let me get it. Let me see if I can't find it. Here we go. Let's work that out here for this table. I'm not saying this is a more efficient way to do this than what's the simple way we just did it, but let's just take a look at this. Okay, probability A given B. In this situation, what is A and what's B in the question I just asked? Right. What's the probability of A? Oops. A given, where's that pipe? There it is. Probability of A given B. Okay. So now, what is A? First of all, what is A? Given B, right? Given B, B was that he's male, right? And what is A? A is that, what was it again? Given that a person is male, given that condition that already occurred, what's the probability he's married? And A is married. Okay. Okay, that would be probability of being married given that he's male. It's probability of A given B. Okay, so let's find out what we have here. What's the probability of A? Probability that he's married. That a person is married. What's the probability of being married in this population? How many people in this population are married? 126 over 214 equals 126 divided by 214. I'm rounding the numbers off. Okay, 20. Okay, probability's married. Okay, so now what else? What do we need next? Probability B. What's the probability he's male? Okay, let's see. What's that? What was it? I can't hear you well up here because of noise from the air conditioning. But so I'm going to go back and look it up. Probabilities male is 104 out of 105 out of 214. Am I right? Okay, good. All right, and what's the probability that he is male, given that he's married. Okay. Oh, well, okay. Let's see. I have to go back here. What's the given that he's married, what's the probability that he's male? That's 62.5 over 126. You guys think I'm doing this okay so far? Okay, so let's figure this out now. So, probability that a person is married, given that he's male, is going to be equal to the probability that he's married, which is this, times the probability that probability that he's male, given that he's married, which is this, divided by the probability that he is male, which is this. And I get 0.604. And what did I get before? Probability that he's married, given that he's male, was 63 over 63.5 over 104. I get the same thing, given that I did some rounding and stuff like that, right? Okay, so I think it worked, right? So this formula gives us the same outcome that we had intuitively on this table. Did that help? I think that's the first time I've done that. Do you think it helped or hurt? It helped a little bit? Okay, but at least you saw that it's true. Okay, that what's in that Bayes theorem actually works when we apply it to this table. Okay, so you don't have to wonder whether or not it's really genuine. Okay? Okay. So I think I got to get you guys a little bit more involved here. How many? So you guys have paper and you have some computers. How about if you open up Excel? And yeah, I want to try and get you guys a little bit more involved. Okay. And if you go onto Blackboard, or you could actually just open up Excel, you don't really necessarily have to go onto Blackboard. If you go onto Blackboard, you'll find let's see, you'll find an Excel file called blank crosstabs. Okay, it looks something like this. Okay, or you could just make that up. You don't need the shaded boxes and outlines and stuff like that. Just make up a box that is a 4x4 table with a header on top that says D plus and D minus and T plus and T minus. Okay, and then these other boxes around it are going to be for totals and things like that. So I think I have a document in here on Blackboard called Diagnostic Test. Next one, number 4, is Diagnostic Test nickel. Okay. So, okay. So I'm gonna discuss a diagnostic test, a new diagnostic test. I've been doing this for a little while because I've been using this particular example for a little while because I found that after, that all of a sudden, for some reason, when I wear watches, the stainless steel back, I start to get a rash from them. And I researched it a little bit, and apparently, but stainless steel is a whole series of metals. It's low carbon steel, it's nickel, it's cadmium, it's got molybdenum, it's got a lot of stuff in it, right? Particularly nickel. Stainless, by the way, I knew a guy who worked for U.S. Steel, right? And they make many different grades of stainless steel, right? Most expensive are the most resistant, strongest, and so on and so forth. But there's a lot of lower grades as well. So you may notice that if you leave some stuff like your grill, which is stainless steel, out, you'll start seeing a little corrosion on it, right? So I mentioned it to him, and he told me that actually with industrial products and stuff like that. And he said to me, well, Tony, you know what we tell our customers when that happens? And I said, no, what do you tell your customers? He says, well, it's stainless steel, not stain-free steel. So, it does corrode a little bit. So that backing on that watch does corrode a little bit from your sweat. So that you get some nickel on your skin. And I think that rash is from a nickel allergy. And nickel allergies are getting much more common because of, implants and piercings and so on and so forth that are made out of various grade steel and stuff like that, and other metals that have, nickel alloyed into them. So that kind of situation get a little more common. So let's say that you're interested in developing a diagnostic test for a nickel allergy. I think traditionally the kind of test that they would use is a patch test. It's like a challenge test. They scratch you and put some compound that contains nickel against your skin with a Band-Aid over it and stuff like that, which is not so good because then you have to, in order to determine that you have that allergy, they may have to make you react to that, right? Which could be dangerous in some cases. So it would be really nice if they had some other kind of test that was less invasive that they could use to determine whether you have a nickel sensitivity. Okay, so let's say that this drug manufacturer decides that he thinks he has a pretty good test to test for nickel sensitivity. And he tests this on people that are known to have a nickel sensitivity, right? They knows that these people have a nickel sensitivity. He finds that 80% of the time, it correctly identifies them as having a nickel sensitivity, right? That's called the sensitivity of this test. This test is 80% effective. The sensitivity is 80%, so 80% effective at identifying this disease, nickel sensitivity, okay? Then he takes people that he knows that have been screened with this other test, and he knows they definitely do not have the disease. Turns out 90% of the time, it confirms they don't have the disease. It correctly identifies them as being negative, not having that sensitivity, that disease, right? That's called the specificity of the test. In this case, the specificity of the test is 90%. Okay? Everybody got on that wavelength here? Okay, sensitivity is how good it is at identifying people who have the disease. Specificity is how good it is at identifying people that don't have the disease. Both of them have some downsides. If it's 80% effective at identifying people who have the disease, that means it's going to miss 20% of the people. And the specificity is 90%. That means 10% of the time it's going to identify people who don't have the disease as having the disease. Okay, so what do we call that? When it gets the test right, identifying someone who has the disease, that's a true positive, right? When it gets it right and identifies somebody who doesn't have the disease correctly, that's a true negative, right? And if it gets it wrong, it's either a false positive or a false negative. Okay, so we're gonna create a crosstabs table, a contingency table, if you want, right? That's gonna look something like this. And so you guys are gonna do this with me. Okay, and I'm gonna start with a population of 1,000 people. Okay, so I'm gonna go down there, I'm just gonna write 1,000 down here. Okay. So I'm gonna say to myself, well, gee, how many people in my how many people out of this population have a nickel sensitivity, right? So I'm going to say to myself, well, let me investigate this. Turns out the prevalence of nickel sensitivity in this population is 10%, right? So out of 1,000 people, how many of them would you expect to have the nickel sensitivity, right? Prevalence is 10%. You'd expect 100 people. How many people would you expect not to have the nickel sensitivity? 900. Everybody agree with me on that? Right? Because this number down here is the sum of all the people that have the disease. This is all the people that don't have the disease out of 1,000 people in this population. Okay, remember what I told you? That I'm going to rewrite it here. The sensitivity was 80%, and the specificity was 90%. Okay, so out of 100 people, what percentage of the time, how many people you think it would correctly identify that had the disease as being positive? Right? And how good is it at identifying? It's 80%. How many out of 100? What's 80%? 80, right? 80 people. We're dealing with whole numbers here. Okay. So how many people does it incorrectly identify as not having the disease? 20, right? So what is that 80 called? That is I'm sensitive, right? But what is that number? That's the true positives, right? That what's in that cell is the people that have the disease and tested positive, true positives. How about the people, these 20 people, what are they? Those are false positives, right? I'm sorry, excuse me. They're false negatives, right? Because what are they? They're negative. They tested negative, but it's wrong. So those are false negatives, okay? So let's go over to our specificity, right? 900 people don't have the disease. How many would we expect to test negative? Well, 90%, right? Which 90% of 900 would be 810, right? You have the right idea, right? Except that you were looking at it from the other 10%, right? How many people we expect that don't have the disease to test negative? We'd expect 810 people. How many people does that leave that test positive? Those are your 90, right? So the 810 is what? Those are true negatives, right? Because they tested negative and they don't have disease. And the 90 are false positives, right? Because they tested positives. Okay, good. Excellent. Okay, so now, what percentage of the people, how many people tested positive? 170. Okay, good. And how many tested negative? 830. And that should add up to 1,000, and it sure does add up to 1,000. So now I'm going to go over here, and I'm going to put something else over here. I'm going to call it the positive predictive value. And I'm going to go down here and say negative predictive value. I'm going to ask you, out of the 170 people that tested positive, how many of them actually have the disease? 80, right? Out of the 107 people, right? Because 80 of them tested positive because they had the disease, correct was correct, and 90 of them tested positive because it incorrectly identified people that don't have the disease as having the disease. So the positive predictive value is equal to 80 out of 170, right? Whoops, somehow I missed that. 80 out of 170, 80 divided by 170 is 47%, right? So in other words, in this population, if you apply this test and a person gets a positive test, it's only about 47% likelihood that he actually has the disease, right? That's what positive predictive value is. What do you think the negative predictive value is? I'm ignoring, you notice we're ignoring the people online here. Let me go online here. Okay, how are you guys doing online here? Oh, yeah, you guys are back by binomial distribution. I must have put you to sleep already. Okay, so negative predictive value. How many of, what do you think the negative predictive value would represent? Okay, let's see. Okay, you got the right idea, right? 810 people correctly, excuse me, 800, excuse me, let me start again. 810 people are negative and tested negative, right? Out of a total of 830 people that tested negative, but don't necessarily have the disease. Total number of people tested negative is 830. 810 of those are correct. So the negative predictive value is 98%. So if you walk away from the doctor's office and he says you tested negative, 98, the probability you really are negative is 98%. But if you walked away with a positive test, then you would say to yourself, well, gee, I'm only about 50% sure, 47% sure that I actually have this nickel sensitivity. That's not really a terrible thing, because what would happen then is he would send you to another test that's more definitive. Maybe then you do the challenge test, the patch test, whatever they call those things these days, right? So he might do a more invasive test or something like that. But it avoided, if all the people correctly predicted, it avoided that necessity to do that more invasive test, right? Now, the only problem is that this is very sensitive to what kind of population that you apply it to. We're going to do exactly the same thing, except we're going to look at a population where the prevalence is only 1%. Only 1% of the population has this disease, right? Okay, so I'm going to put 1,000 in here. I'm going to use 1,000 again. Out of 1,000, what's 1% of 1,000? 1% of 1,000? 10. Okay. Okay, and so how many people? That would mean 10 people out of 1,000 have the disease. How many people don't have the disease? 190. Okay, given the same sensitivity, right? Sensitivity is 80%, and the specificity is 90%. Given exactly the same test applied to this other population, right, we're going to demonstrate two things here. That the prevalence is very important, and the sensitivity and specificity of the test is independent of the prevalence. It's a nature of the test, right? But the prevalence is going to influence something else dramatically. We're going to take a look at that in a second. Okay, so if 10 people have the disease and the specificity is 80%, how many people do we correctly identify as having the disease? Out of 10. I'm hovering here waiting for an answer. 8, right? 8 people, right? You got 10 people that have the disease. The test gets it right 80% of the time. So 8 people have the, you're going to correctly identify 8 people as having the disease. All right, you know what I'm going to do? I'm going to write in here as I do this. This is true positives. This is false negatives. This is true, excuse me, false positives. And this is true negatives. Okay, good. You have to think about it, right? Okay, so here, this would be 8 people. And that leaves 2 people that have the disease that were incorrectly identified as false, as negative. Okay, so out of 990 people, how many, 90% accurate test, how many people would we expect to be correctly identified as not having the disease? You know, I'm going to do false positives here first, because that's going to be 10% of the 990. So that's going to be 99. It's easier to calculate. And how many would that leave here? It would leave 891. Okay, so we add these together. So how many people tested positive here? 107. Oops. 107. How many people tested? Oops. I can just write in the 107. How many people tested positive here? A negative here? 892. 893. Adds up to 1,000. Now let's calculate our positive predictive value and our negative predictive value. Okay, so what's our negative predictive value equal to? How many people tested positive? 107, right? Out of those 107, how many of them actually have the disease? 8. So it's 8 over 107 is equal to 7%. And negative predictive value is going to be equal to 891 divided by 893. So it's even higher. You know, it's I'm not going to format that. It's really more than 9. It's rounded it off to 1, but it's really 99.99 something. Okay. So what happened to the positive predictive value? 7%. Most people that test positive, as a matter of fact, 93% of the people that tested positive don't have the disease. The test didn't change. The effectiveness of the test didn't change. Specificity didn't change. The sensitivity didn't change. What's the only thing that changed? The prevalence of the disease in the population. Why did this happen? What happened here? What made this occur? Right? Well, what happened to the number of true positives that we had? The prevalence that went down. We didn't have as many true positives, did we? So the numerator got smaller, right, in positive predictive value. What happened to the denominator, the total number of positives? Well, that got smaller, but look what happened to the false negatives, right, or the false positives. They went way up because we were testing so many people, so many more people that don't have the disease. Even though the sensitivity is very good, we still wound up with a situation where we found there were just so many people being tested that we got a lot of false positives from that, right? And as Levi was discussing, there's a lot of diagnostic tests that are like this. They have very good sensitivity, very good specificity, but the prevalence of the disease in the actual population might be very low. So particularly if you pick out if you target a population where they're not like they're in an age group or they're some other group that's not likely to have that disease. So if only, at a specific time when you're applying this test, if only 1/100th of 1% of the population has a particular disease, even if the specificity and sensitivity is very high, you're going to get an enormous number of false positives. And you know that's true because you have in pap smears, you have a lot of false positives. PSA tests, you wind up going for more invasive testing and tracking and so on and so forth because there's so many false positives and so on. Why? Because that cancer is relatively rare or low in the population, and prostate cancer is, especially before you get to a certain age, is relatively low percentage of the population, low prevalence population. So if you test everybody, you wind up with these kind of results. Okay, now what kind of probability is the positive predictive value? What is the positive predictive value? The positive predictive value is the probability you have the disease given that you tested positive. The positive predictive value is the probability you have the disease given that you have tested positive. What kind of probability is that? It's a conditional probability, right? Just like we did before with that table, it's exactly the same kind of thing. Remember that nasty formula we were looking at before? Bayes' theorem, right? Let's bring that back up again. I think I might actually have a version of this table with that on there. I'm going to close this. I'm going to go back here. Let's see. Okay, here we go. Okay, so what I got here. This is calculating it all. I don't want this. I don't want you to see that. Don't look at that. Hang on a second. I want to go either one of these two. Okay. I want this. Can I get that? Why wouldn't let me select that? Hey, okay. I'm gonna go online. Get a copy of that for me. Oh, beach ball. Where's a good version of this? Okay, we got that already. We don't need that. I want the Bayes theorem. Come on. I know I have it here somewhere. Oh, look. That. Oh, okay. I'll take that. Very strange people in statistics. Formula should be in there somewhere, I guess. There it is. Okay. I'm going to steal that formula, put it over here. I think I put it over there. Get rid of this. Strange things can happen when you go on the internet without being prepared, right? Okay. Okay, I'm going to open that up so we can see it. Okay. Probability of A given B has occurred. The probability that you have the disease given that you've tested positive, right? So what is A? A is the probability you have the disease. B is the probability that you is test positive. So A is disease, B is the results of the test. So if you look at this formula, what it really breaks down to, okay, what it really breaks down to is, let's see, we have one part on top and two parts down on the bottom. Okay, on top we have the sensitivity times the prevalence. Okay, so let's think about that. The sensitivity is 80%. I'm going to work with our first example, 10% prevalence. Sensitivity is 80%. The prevalence was 10%, right? 80% times 10%, right? 80%, 10% of the people have the disease. 80% of the time we'll correctly identify them with this test. That's the sensitivity. So 80% times 10% is 80% times 10% is 8%, right? 0.08. Am I right about that? 0.08, right? 0.8 times 0.1, 0.08, right? 8%. That's the percentage of the population that test positive, that have the test positive, that have the disease, right? That's the percentage of population that test positive, that have the disease. Right? Those are our true positives. Down on the bottom, we have 8%, it's the same thing, 8%, our true positives, right? So now we need to add to our true positives our false positives, right? Remember, that's how we got our positive predictive value, is we said, oh, it's going to be the number of people that test positive that really have the disease divided by the total number of people that test positive. So on the top, we have the percentage of people in the population that tested positive, right, that have the disease. And we have it again here, total, the percentage of people that have the disease test positive. Plus, so this other part must represent the percentage of people that don't have the disease that tested positive. Well, how do we get to that? Well, first of all, we got 1 minus the specificity. What was the specificity? It was 90%. 1 minus that is 10%. This is the percentage of time that we get it wrong on the people that are negative. We get it wrong 10% of the time. Minus times 1 minus the prevalence. So 10% of the time we get it wrong on people that don't have the disease. Times 1 minus the prevalence, that would be 90%, right? Because 10% of the time the prevalence is only 10%, would be 90%. So 90% of the people don't have the disease. We get it wrong 10% of the time, right? So if we multiply those, we get the number of people that don't have the disease that test positive, the percentage of people in the population that test positive. So on the bottom, when we add these two together, we get the total number of people that tested positive, whether it's a true positive or a false positive, and on top, we have the total number of the total percentage of people, total number of people, percentage of people that test positive really have the disease. Exactly the same thing that we did when we used the table. Do you have to think about this as you apply this? No, I'm just explaining it to you so that like you understand that this formula is doing the same thing that you did intuitively with that table with the populations that you just did, calculating the positive predictive value on your diagnostic test table, that crosstab table, right? It's doing exactly the same thing. Let's apply it. Let's apply it to the first one that we did. Okay, if I can still find it. Do I still have it? Yeah, let's apply it to this. We said positive predictive value is 47%. Okay, let's apply this formula. So on the top, we have, okay, oops, escape. So I'm going to go over here and I'm going to say what's on the top of this equation. It's equal to the sensitivity, which was what, 0.8, times the prevalence, right? See prevalence there? And what was the prevalence? The prevalence was 0.1, right? 10%. And that comes out to be 0.08. So what's on the bottom? Well, on the bottom, we have to add together this again equals 0.08. I'll just put I'll just put 0.08 in here, right? If you look on the bottom, it's the same thing, isn't it? Sensitivity times the prevalence, right? It's 0.08. Those are 8% of the people are true positives, right? 8% of the people are true positives down there also. Now we have to add to it the false positives. How do we calculate that? That's equal to, oops, 1 minus the specificity. What's the specificity is 90%, right? Well, 1 minus specificity is, whoops, is 0.1 times 1 minus the prevalence. And the prevalence was 10%, so this would be 0.9. And that comes out to be 0.09. So now I add these two together and put that in the denominator and put this in the numerator. Let's see what I come up with. Equals 0.8 divided by the sum of these two, this plus this. Right? And that's that formula. And I come up with the same positive predictive value. Okay? So if you saw this formula on an exam, and I told you the sensitivity and the prevalence, you would be able to calculate the positive predictive value. And if you didn't feel comfortable doing that, you could go back and you could recreate this table from that information, right? All you have to do is put in a big number down here for the population. Prevalence gives you that number, and 1 minus that gives you that. This minus that gives you that. And then since you know the sensitivity, you can fill in that and that. Since you know the specificity, you can fill in that and that. And then you can calculate that and that. You can figure out what the positive predictive value, the negative predictive value, using this table to check if you did that formula correctly. Or if you did it this way, you could then use that formula to check to see if you did the table correctly. Any questions? No? No questions at all? Sure. I'm sorry, say it again. The prevalence? Yeah. Well, Bayes, the Bayes theorem applies to many situations. We're just applying it to this, right? It applies to anything where there's a conditional probability, right? We're using it specifically for calculating the positive predictive value for a diagnostic test. In our case, we were looking at the probability that a person actually has a disease given that they've tested positive. But then you could use it in a million other situations. It's just that A and B, are other things, right? Just like in the other one, just like in that table, we were looking at it from the perspective of the probability of being married given that you're male, or male given that you're married, or something like that, right? You can use Bayes' theorem universally. We're just specifically applying it to this. Okay, how are you guys doing online? Are we going to calculate? Actually, you can. If you look at that, there is another way to calculate negative predictive value. And if you look at this carefully, what you got there is you got the number of people, the proportion of the population that tested negative, that are really negative, that are true negatives on the top. And on the bottom, we got the total number of people that tested negatives, false negatives, and true negatives. Right? So it's just the way you would look at any kind of probability question. Yes? Why don't you come up here and repeat that? So it'll be in the record. It'll be in the recording, and the guys online can hear. All you have to do is be in the vicinity of the.
Sorry, I was just answering with a little more.
You might repeat the question. They probably.
The question was, how does Bayes' rule relate to Bayesian statistics, which you probably heard about. And Bayesian statistics is concerned about the probability of models given the data, and calculating that from something you can calculate, which is the probability of the data that you see given the model. And in Bayesian statistics, that probability of your data given the model is called the likelihood function, and then you go through calculating Bayes' theorem to go from a prior probability of your model based on some assumptions, or a so-called uninformative prior, to your posterior probability of that model given the data that you've observed, and they go through these same calculations except in way more complicated situations, and with likelihood functions that you can only do computationally to estimate the probability of different models given the data that you have, more or less.
What course number is that?
Yeah, we don't have a Bayesian stats course.
Oh, okay,
here.
there you go.
So, but I guess as a plug, I do the statistical learning book club, and we have in the past done a Bayesian stat textbook, just as another way.
Okay, and that's another reason for them to join your book club, because these are guys that are going to be taking advanced statistics courses here as well. So
other stuff that isn't covered in the
course.
Okay. And in a way that doesn't involve exams.
Okay, there you go. Yes, that's correct, and probably not having disease that they've tested. That's a negative predictive value. That's a good description of negative predictive value. Good. Okay. So just question being answered there online. Okay. So let me see what I had here besides this that I wanted to make sure I covered. Oh, and I had set up another table here that you have online that that you could use kind of to fill in the table backwards. So if you're stuck on a problem like that, you know the sensitivity, specificity. If you're given the prevalence, the sensitivity, and specificity, you could then backfill the table the way I kind of created in the beginning, calculate the positive predictive value and negative predictive value. So I want to cover two more things that are a little. First, I want to go over something that came up. A few questions came up online on SPSS and in the forum. And I also want to, I think we had that Venn diagram question that we were talking about before. So let me just open up SPSS for a second. Okay, I'm going to use the student test score, the very simple student test score document that I think you guys use that, right? On the assignment student test scores. When I usually present this, when I talk about descriptive statistics, I usually tell people, you know, if you want to do basic descriptive statistics, you're going to do analyze, descriptive statistics, and then you have a number of choices. You have frequencies, descriptive statistics, explore. If you go into descriptives, it gives you just the basic descriptive statistics. You can actually go into the options, and you can check off what you want. And I think in the assignment, I mentioned you might want to provide the mode, which, to tell you the truth, with numerical variables may not be that important, but you know, maybe something you might be interested in. You may notice that's not one of the choices here. There's a lot of stuff that's not here. If I click OK, my output oops, I didn't move the variable in. If I click OK, the output window opens up and it gives me some basic statistics, the minimum, maximum, the range, the mean, standard deviation, the variance. And I mentioned to you that if you went further, you went into descriptives and went into explore, you would get more information. you would get, if you went in here, it would assume you'd just be telling it that you want descriptive statistics. It would choose them for you. And then it could give you some other information as well. You in plots, you could ask it to do a histogram and so on. I'm going to click continue. I'm going to move this variable in here. And also there is the possibility you could also use that to break up data into different groups. But you can see you get a bit more descriptive statistics, but you still don't get the mode, right? Usually, I've been suggesting that students use analyze descriptive statistics frequencies for categorical data, because it'll do a table where it counts like how many males, females, how many different ethnicities, put it into a nice table for you, and so on and so forth. But you can also use it for numerical variables as well. So if I move this in here for the variables, right, even though it's kind of really this function kind of really targeted towards categorical variables, it is used with numerical variables also. If you click on statistics, you can here ask it to calculate quartiles, calculate percentiles. If you click that one, it'll give you all the 10th percentiles, all the 10 percentages, 0, 10, so on and so forth. Mean, median, mode in this case, and so on, and standard deviation variance. So you have some other stuff you can get from here. I click OK, and click OK here. And sure enough, here's all my statistics. Now you'll notice something interesting. It is an asterisk next to the mode. Anybody want to hazard a guess why it's an asterisk? More than one mode, yeah. And it actually gives you only the first one in SPSS. Right? So just so you know it, and if you do a histogram, you might get lucky and see, here you go. Here's the reason why it came up with 2 modes. Right? And that, that can change also depending on how the numerical variables, depending on how wide these bins are, that might actually change. Right? You might get fewer or more modes. Right? So that has some impact on it because it determines how many people are in each bin. So make them wider, might change things. Make them narrower, the shape of this might change a bit. Okay. So if it does come up, now you know a way you can get the mode if you really, really need to get it. And if you left it off the assignment, I'm not worried about it because I don't know how useful this kind of mode really is anyway. Okay. So, and then finally, let's talk about, let me get a blank piece of paper. I'll close that. Okay, let's see if we can do this without messing this up. Okay. Okay. So I have this upside down U. What is that called? Intersection. And this one is union. Okay, and basically in English, what do we mean by intersection? It means it's got to be both, right? It's A and B, right? Not just A, not just B, but A and B. And union, we mean A or B, right? Okay, good. All right, good. So let's say I'm drawing something like this. This is A. This area in here represents A. And this is the rest of the universe here. This area represents B. And this area out here is not A and is also not B, right? Because it doesn't contain A or B. Okay, so what area would be contained in the union of A and B here? Well, it'd be everything in here plus everything in here, right? Okay. What would be contained in the union of A and not B? Right? Will that be what's in here and whatever's not in B as well? Let me try another piece of paper here. let me have these overlap a bit. Okay, if I were to shade all of this, okay, this is B, and this is A. This is B, and this is A. Okay, what will we call that? Right, that'd just be B, right? Okay, what would we call this area in here? That's A intersection B, right? It's both. What will we call this area here? A? Oh, A minus, we don't really say minus though, right? A and intersection, how about it's not B, right? How about B complement? A intersection, not B. Okay. So in other words, this represents the area which is A and not B at the same time. So that leaves this part out. So that means that only this part is included. So that not B, that complement, is that it's not, it doesn't include that, that it's in any area that doesn't include that. Let's see if I can try another one here. Let's see. Okay, how about this area? I'm freestyling here now. I'm not sure if I'm going to get this right. How about this area here? Hey, Levi, what do you think this, if I was looking for just A and B without the intersection, well, then I would subtract, I guess. This would be A plus B minus A intersection B, right? I think, right, okay. And how about, more room here? Oops. Let me start with a new page. Do one more. And A intersection B. What is this area out here? That would be not B and be not A, right? So we could, I presume, call that union of A and not B, not A and not B, right? Because if we just said not A, it would include B. If we just said not B, it would include A. So this is the intersection, union or intersection, union intersection. It's got to include both those conditions. So it has to be both not A and not B. So this area out here would be A complement intersection B complement. Okay? So basically, all the complement really represent is does not include that area, that probability. Okay. Any other questions on SPSS, the assignment, or any other stuff? Because I think I'm going to be posting an assignment on conditional probability, on the diagnostic tests, and maybe a few of these other things. Maybe I'll try and find some examples of Venn diagrams that you guys can practice on. Because the test probably will have, even though it's annoying, the test will have some of these everything. Okay. All right. So I guess we're pretty close to 7:50. I think we can call it a night. Any questions before we split up? Any questions on the assignments? Yes. A little confusing. That's okay. Oh, what was that? Yes? Well, they're both conditional probabilities, right? They both describe an outcome based on some other outcome having occurred before it, right? Or having already occurred. So base theorem always works with a conditional probability. And this particular conditional probability was that the person tested positive, right? So we have a specific, Bayes works in a lot of different areas. In this particular application, it was always going to be either a positive or negative test outcome, right? Either negative predictive value, which is a conditional probability, presumed a negative test outcome, and the positive predictive value presumed a positive test outcome. Okay.